Human speech carries a massive amount of data in every syllable. Beyond the literal message, a single spoken sentence encodes the speaker's age, emotional state, and physical identity, encoded into a dense, time-varying acoustic signal. For decades, audio engineers have faced a significant challenge: translating that biological output into a mathematical format that machines can process. A mechanical siren emits a steady, predictable tone. The human voice, however, is highly volatile. Its acoustic properties shift drastically from 1 millisecond to the next. Look at this raw speech waveform, plotting amplitude over time. Trying to extract meaning from this unbroken, jagged line is the core problem in speech analysis. As we scan across 1 second of audio, the signal is constantly morphing. Because the mouth's physical structure moves, the sound waves are inherently non-stationary. Notice the dense, high-amplitude repeating clusters, immediately followed by low-amplitude, scattered noise. To apply machine learning to this biological chaos, we cannot process the raw audio file as a single block. We must mathematically deconstruct the wave into distinct, extractable features. To reliably extract those features, engineers map the physical anatomy of the human vocal tract directly to a signal processing equation. This framework is called the source filter model of speech. It divides the vocal system into 2 distinct mechanisms. One generates the raw acoustic energy, and another shapes that energy into recognizable sounds. By tracking this biological to mathematical pipeline, we eventually uncover a distinct auditory paradox: situations where the human brain actively perceives frequencies that do not exist in the physical data. Building accurate machine learning models requires bridging the mathematical reality of the raw signal with the biological illusion generated by the ear. The production of a voiced speech signal begins with a biological battery. The lungs expel a column of airflow upward through the windpipe. Air hits the larynx, where the vocal folds snap close. The pressure forces the folds to rapidly open and shut in a repeating cycle. This rapid, repeating vibration creates what we call voiced sounds, which include all vowels and specific consonants like M and Z. Here is the resulting source signal plotted on a graph. The physical snapping of the vocal cords translates into a series of repeating, quasi-periodic acoustic pulses. By measuring the time duration between 2 consecutive peaks, and taking the mathematical inverse of that number, we calculate the fundamental frequency, or F0. Because this system is driven by organic tissue, the physical vibration is never perfectly periodic. These micro-variations in the period length from one cycle to the next are known as jitter. Likewise, the amplitude of each pulse is not perfectly uniform. These micro-variations in the height of the pulses are known as shimmer. Despite these biological fluctuations, the vocal folds successfully generate a measurable fundamental frequency, along with a cascading series of higher integer harmonics. At this stage, the raw, buzzing source signal is unintelligible. It still has to travel upward through the throat, the mouth, and the nose. Combined, these anatomical cavities act as a highly dynamic biological filter. This spectral plot demonstrates the mathematical result in the frequency domain. The blue vertical bars are the raw source harmonics. The smooth red curve overlaying them represents the biological filter, which boosts specific frequency bands while suppressing others. This gives us the foundational equation for speech processing. Speech equals the source multiplied by the filter. Look at the highest resonant peaks created by that red filter envelope. Engineers call these amplified frequency bands formants, labeled F1, F2, and F3. Moving your tongue and lips physically alters the shape of the biological filter. This shifts the placement of formants, allowing you to produce distinct vowels. While the vocal folds provide raw acoustic energy, the vocal tract's filtering action dictates the actual phonetic data required for machine speech recognition. That model holds true for vowels, but it behaves entirely differently when analyzing consonants like the S or F sounds, known as fricatives. During these unvoiced sounds, the vocal folds remain open. The lungs force air through tight anatomical gaps in the teeth and lips, creating shear turbulence. Here is a split-screen plot comparing the two. On top, we have the rhythmic, high-amplitude waveform of a voiced sound. On the bottom is the waveform for an unvoiced sound. Notice the complete absence of any repeating pattern in the bottom wave. There is no fundamental frequency here. It is a chaotic, low-amplitude, noise-like excitation. A comprehensive speech processing model must dynamically switch between tracking strict harmonic frequencies and analyzing this turbulent, non-periodic noise. Generating the physical sound wave is only half the equation. The other half is how that wave is perceived by the human listener. Physically, the fundamental frequency is a measurable quantity in hertz. However, pitch is the purely perceptual sensation of that frequency. This graph plots actual frequency in hertz on the x-axis against human perceived pitch, measured in mels, on the y-axis. It proves the brain does not interpret frequency increases linearly. At lower frequencies, the relationship is nearly linear, but as the frequency increases, the curve becomes severely logarithmic. A jump of 500 hertz at the low end sounds like a massive shift in pitch, but the exact same jump at a higher frequency is barely perceived by the listener. This nonlinear processing is a direct result of the biological hardware in our inner ear, specifically the cochlea. Inside the cochlea sits the basilar membrane, an organic frequency analyzer. As sound waves enter, they cause specific locations on this membrane to vibrate. High frequencies trigger a response at the rigid base of the membrane, while low frequencies travel all the way to the flexible inner apex before resonating. Pitch identifies the specific physical location of an active neural trigger along that organic membrane. Because the brain maps these physical neural triggers, the system is vulnerable to auditory illusions, which engineers can expose using a specific signal processing experiment. Consider this spectral plot of a voiced speech signal. You can clearly see a tall fundamental frequency spike resting at 93 Hz, followed by a series of descending integer harmonics. Now, watch what happens if we actively strip away the acoustic foundation of this sound. By applying a 450 Hz high-pass filter, we mathematically erase the 93 Hz fundamental frequency and all the lower harmonics. That physical data is completely gone. The new lowest frequency remaining in the modified data is the harmonic sitting at 465 Hz. Yet, if you play this modified audio file to a human listener, they will still perfectly perceive a pitch of 93 Hz. The brain analyzes the exact mathematical spacing of the surviving upper harmonics hitting the basilar membrane. Detecting the uniform gaps, the brain retroactively deduces the missing root frequency and fills in the blank. The human auditory system actively hallucinates missing data to maintain continuity. Successful audio modeling requires mapping the physical reality of the signal alongside the evolutionary quirks of the biological hardware interpreting it.